Hello, previously we have learned important concepts such as instantaneous power and average power, and we also learned the effective value of a waveform which we called root mean square value. Now in this lecture we will build upon these concepts and define complex power. Previously we learned that linear circuits with sinusoidal inputs at steady state will have all the voltages and currents of the elements as sinusoidals with the same frequency of the input. We also learned that we can analyze such circuits in the frequency domain using phasors and impedances. Now we will learn how to calculate power generated and absorbed in a circuit with such elements, and this is called complex power. Let us assume we have the phasors V and phasors I for voltage and current respectively. The complex power delivered to an element is defined as S is equal to V times I conjugate divided by 2. And accordingly, when we just put the phasor for V and I to this equation, we end up with the magnitude Vm times Im divided by 2. And angle theta V minus theta I. Remember, this is very similar to the average power which we were calculating when we were dealing with sinusoidal voltage and current sources. Here, I star denotes the complex conjugate of the current phasor I. Complex conjugate means that we take the imaginary part and make the plus minus. The magnitude S is equal to Vm times Im divided by 2, and this is called as apparent power. Let us convert the complex power from polar to the rectangular form. Here we have it in the polar form, Vm times Im divided by 2 with an angle theta V minus theta I. In the rectangular form, we have the real part and we have the imaginary part. The real part here is equal to the average power, and we can represent S in the form of a rectangular representation. S is equal to P plus JQ. Here P is the average power and Q is called the reactive power. So reactive power is not really there, but it is actually causing fluctuations in the power flow, and therefore it needs to be taken into account, for instance, to balance different transmission lines. In general, the average power has the units of watts, the complex power has the units of volt amps, and reactive power has the units of volts amps reactive. This is basically important jargon or terminology for power engineering. The impedance of an element is expressed as the ratio of the voltage phasor to the current phasor, and it can be given as Vm divided by Im times angle theta V minus theta I. We can also represent this in rectangular format as R plus Jx, and here R is this term and X is this term, and we can get these from the Euler's relation, because we could have written this as Vm over Im times e to the j theta V minus theta I. And from here I could have used the Euler's relation to write it as in the right part of the equation 1. Now let us remember, in the previous slide we found the complex power in the rectangular form as this. And when we look at this expression for R is hidden here, and this expression for the X is hidden here as well. Therefore we can represent the equation 2 in terms of the impedance 1 as this. S is equal to I squared M divided by 2 times real part of the impedance plus J times I squared divided by 2 times the imaginary part of Z. So basically this is something very similar to the I squared times R, But here we are dealing with phasors and impedances. And the average power delivered to the element is only due to the real part of the impedance, which is the resistive part, and therefore it can be written as P is equal to Im squared divided by 2 times real part of the impedance Z. The average power delivered to an element is given with this equation. And if this element is a resistor, in other words, our impedance is only R, then the real part of this is obviously just R, and this expression becomes for a resistor Im squared divided by 2 times R. So we basically have energy dissipation over an resistive element, and the element therefore absorbs power. But if we have an inductor or capacitor, the real part is equal to 0, and therefore the average power absorbed by these elements is also equal to 0. And let us remember here the impedance triangle. Here we have the real part, here we have the imaginary part, the magnitude is Z and angle is theta. And similarly, we can have a complex power triangle where we just have here P, we have here the imaginary power Q, here we just have the complex power magnitude S, and here we have the angle theta. The circuit shown on the right consists of a source driving a load. The current source is I of t is equal to 1.25 times cosine 5t minus 15 degrees amperes. Now in the A part of the question asks us what is the value of the complex power delivered by the source to the load when R is equal to 20 ohms and L is equal to 3 henries. And in the B, the question asks the opposite. What are the values of the resistance R and inductance L when the source delivers 11.72 plus J 11.72 volt amperes to the load? Let's start by solving part A. We need to start solving this question by finding the combined impedance Z, and Z will be equal to ZR in parallel with ZL, and this will be equal to 1 over R plus 1 over J omega L, and accordingly this will be equal to J omega L R divided by R plus J omega L. And if we plug in the values, we will find J times 5 times L is 3, R is 20, divided by 20 plus J times 5 times 3, and this is equal to 300J divided by 20 plus 15J, and this is equal to, when I just do some complex algebra, 12 with an angle of 53 degrees ohms. So I found my impedance. Now, in order to find the complex power, in addition to the current, I need to voltage phasor. Voltage is equal to I times Z. This is equal to 1.25 times with an angle of minus 15 times 12 times 53 degrees, and accordingly 1.25 times 12 is 15, and 53 minus 15 is 38, so it is 15 times 38 volts. This is my voltage phasor. And after I find this voltage phasor, next I need to find the complex power, and we had defined it previously as V phasor times I phasor conjugate divided by 2. So what is V? 15 times 38 degrees divided by 2 times I conjugate. I is 1.25 with a minus 15 degrees angle. So I will just make it plus 15 degrees. And accordingly, this will be equal to 9.375 times 53 degrees. So this is basically with the units of volt amperes, since it is complex power, the complex power delivered to this load. I can find the apparent power and reactive power out of this as well, if it would be asked by the question. What are the values of resistance R and inductance L when the source delivers 11.72 plus J 11.72 volt amperes to load? So what do I know? I know that S is equal to 11.72 plus J times 11.72. For convenience, let me write this in polar form, and that will be equal to, if MATLAB tells me, right, 16.57 with an angle of 45 degrees. What else do I know? I know the phasor for I from here. It is 1.25 times with an angle of minus 15. What else do I know? I know that complex power S is equal to V times I conjugate divided by 2. From here I can get V as 2 times S divided by I conjugate. And this will be equal to 2 times 16.57, 3304 with an angle of 45 degrees divided by 1.25, and the conjugate means that I need to make the minus 15 degrees plus 15 degrees. And this will be equal to 26.5 with an angle of 45 minus 15 is 30 degrees. Now I found V. And before I calculated that, Z, the impedance, is equal to V over I. And what was Z? Z in my case was 1 over R plus 1 over J omega L. And we remember that we had admittance, which is 1 over Y. And accordingly, Y is equal to 1 over R plus 1 over J omega L. So Y is at the same time equal to I divided by V. So if I find I divided by V and equate this to this, I will have I divided by V is equal to 1 over R plus 1 over J omega L. So I know I found V. So I over V is equal to 1.25 times minus 15 degrees divided by 26.5 times 30 degrees. Let me clean the board and find this quantity. And this is equal to 1 over 21.2 times 45 degrees, which is equal to 0.033 minus J times 0.033. Now, let's do some complex algebra. This is the real part, which corresponds to this. This is the complex part, which corresponds to this. I will equate these to each other and find the values of R and L. So accordingly, I have 1 over R is equal to 0.033. And from here, I find R is equal to 30 ohms. Similarly, minus J over omega L is equal to minus J divided by 30. From here I get omega L is equal to 30. Omega is 5, and therefore I find L is equal to 6 henries. So basically I found the values of R and L for the complex power of 11.72 plus J times 11.72 volt amperes to be delivered to the load, which consists of a parallel R and L branch. Complex power is conserved. the sum of complex power received by all elements in a circuit is equal to 0. Since we are right now dealing with a complex quantity consisting of real and imaginary parts, this statement should be true for both of those components. So in other words, the sum of all real part of the power received by all the elements should be equal to 0, and the sum of all imaginary power received by all elements should be equal to 0 as well. Here V and I are phasors corresponding to the different elements in that circuit. The complex power supplied by the sources in a circuit should be also equal to the complex power absorbed by the elements in that circuit as well. So we can just write the statement here in this way as well. Okay, here we need to verify that the complex power is conserved in the circuit with the input Vs is equal to 100 cosine 1000 t. So how should I approach this? I think I will find the complex power delivered by the source and see whether that is equal to the sum of the complex power delivered to the resistor, inductor, and capacitor. And in order to do this, I need to first find the phasor for I. But before doing that, I need to convert this circuit to the frequency domain and find the R, L, and C as a combined impedance. Alright, for the voltage, my phasor will be 100 with an angle of 0. The resistance is 10. Here the inductor will be J omega L. Assuming that omega is 1000 and J is equal to 20 millihenries, here I have 20J. And here similarly I will have minus J over omega C. And omega is 1000 and C is 100 microfarad. So this will be, if I am not wrong, minus 10J. Therefore, the combined impedance here will be all of these added together. So it will be 10 minus J 10. And this will be in polar format. 10 times square root of 2 times, here it is plus 10. 45 degrees. So now I want to find the current I, the phasor for current I. I will be equal to V over Z, and V is equal to 100 with a 0 degrees divided by 10 square root of 2 times 45 degrees, and this will be equal to 5 times square root of 2 times minus 45 degrees. So this way I found my current I as well. Let me continue by finding the complex power delivered by the source. So that will be SV is equal to V times I conjugate divided by 2. And this will be equal to 100 with an angle of 0 times 5 times square root of 2 times minus 45 will be plus 45 because it is the conjugate divided by 2. And now I will use MATLAB in order to find this quantity, and it is 500 times square root of 2 sevenths, okay, is equal to 353.5 with an angle of 45 degrees. Now we found the power delivered by the voltage source, the complex power, and we need to see whether the other three elements will absorb the same amount of power delivered by the source to make sure that the complex power is conserved in this circuit. Okay. In order to find the power delivered to each element, I need to first find the voltage of each element. The voltage phasor for the resistor R will be simply 10 times I. I is 5 times square root of 2 with 45 minus 45 degrees. And this will be equal to 70.7 times minus 45 degrees. And secondly, for the voltage for the phasor for the inductor is equal to j omega L, which we found here already, the impedance of that element, 20J, times the current, which is 5 times square root of 2 times minus 45. I know that J corresponds to plus 90 degrees, so the result will be 141.4 times 90 minus 45, 45 degrees. And similarly, the voltage for the phasor for the capacitance will be equal to minus J10 times the current, 5 times square root of 2 minus 45 degrees, which is equal to minus J is minus 90 degrees. Accordingly, 70.7 times minus 90 minus 45 is minus 135 degrees. Now I found the three voltage phasors, and I can use this plus the current I in order to find the complex power absorbed by each of these elements. Let us start with the complex power of the resistor. SR is equal to V times I conjugate divided by 2, and this is equal to 70 VR here, 70.7 with an angle of minus 45 times 5 times square root of 2 times plus 45, because this is the complex conjugate, divided by 2, and this is equal to 250 with an angle of 0 volt amperes. Similarly, SL is equal to VL times I conjugate divided by 2, and this is equal to 141.4 with an angle of 45 degrees times 5 times square root of 2 times 45 degrees. So 45 plus 45 is 90 degrees, and 90 degrees is J. So I can accordingly write this as 500 times J volt amperes. And similarly, SC will be equal to VC times I conjugate divided by 2, and this is equal to 70.7 with an angle of minus 135 times 5 times square root of 245 divided by 2, and this is equal to, accordingly, 570, 500, 250 times minus J, because we have minus 90. And we found this way the complex power delivered to resistance, inductor, and capacitance. Now let us add all the power delivered to SR, SL, and SC. SL plus SR plus SC is equal to 250 plus 250J, which is equal to 353.5 with an angle of 45 degrees. And voila, this is exactly equal to the power supplied by the voltage source. And therefore, we can conclude that the complex power was conserved in this circuit. We are done.